Lots of people do this experiment using a solid-state Tesla coil. They have one wire coming off the bottom of the coil leading to a transistor. The other wire off the top of the coil leads to a test light and maybe a multimeter to measure frequency. When they put on 10 volts, a couple watts, and they attach one wire to the base of the transistor like that, the light lights up, which is really cool. And you get about 532 kilohertz. That's fine. The trouble is this wire gets extremely hot and can burn the hell out of you. So what we're going to do today is look for little tricks of how not to burn yourself or your transistors when working with resonant Tesla coils. Now here's the circuit we're talking about in the schematic sense, which many people use. It can get very hot. We have a DC power supply here, plus minus, a voltage divider here, 3.3K or 1000 K ohms, a transistor here, a base collector emitter, a primary coil and a secondary coil, 16 on the primary and 1000 on the secondary, about 0.5 millimeter wire. So what happens is when we put a pulse of voltage into the primary coil, the secondary coil reacts in a lens sense in the opposite way and sends out a reverse pulse. Some of that goes to this light over here. Some of it goes back into the base of the transmitter there, and then makes this transistor flip on and off about 500,000 times per second. And this is a very high frequency light. Now that's wonderful, very elegant, and the trouble is this wire over here can get very, very hot. If I touch it now, oh shit, it's going to burn me. So here, even at 10 volts you can get burned very easily. So how can we do this experiment more safely? I found several interesting and simple ways to do this more safely so you don't burn yourself and you don't burn out the transistor. The last thing you want to do is put a lot of hot energy into your transistor. The first way I'm going to show you, you take the wire from the bottom of the secondary coil, which can get very hot here, the feedback wire, which often goes into the base of the transistor. Instead of that, you rig this little iron bar here of 10 millimeter with about 20 or 30 turns of 10 amp auto cable wire. It's very simple. It's all insulated. And you just twist all those turns of wire on it, and then you connect one end of that wire through a 0.47 nanofarad capacitor back into the base. Now what happens is, if you take the feedback cable and just touch the iron, not anything else, it turns the light on by the magnetic field, and you get about 708 kilohertz. If you touch the wire itself, insulated wire, you get nothing. So if you do that, the power going into this thing is very safe and won't burn you at all. You can hold on to it all day. That's one very safe way to do it. You can also connect the feedback cable from the bottom of the secondary coil into this 20-30 turns of insulated 10 amp wire wrapped around the iron bar. Now when you take the connection to base to a 0.47 nanofarad capacitor and touch the iron in a reverse sense like that, it still lights up the same way. So it doesn't matter how you do it, it works the same way by induced magnetic fields in the iron, and the energy going into this transistor is no longer very hot, but safe and easy to touch and hold on to. I'll show you on a schematic diagram what we've done. I call this a cold circuit, which won't burn out your transistors or burn you. Have the same DC power supply, the same voltage divider, the same primary and secondary coils, the same wire to the light. But now the wire from the secondary coil, instead of going directly into the base of the transistor here, we make a little iron bar 10 millimeters thick, 20 to 30 turns of just 10 amp auto cable, insulated, very commonly used, and put that through another little connector wire through a 0.47 nanofarad capacitor into the base. Now that works perfectly, and you get the same power, same everything, but you don't get burnt because the voltage coming out of there is a lot less than the voltage coming out of the primary coil. So your transistor stays safe and you don't get burnt. Suppose that you don't have a piece of iron 10 millimeters, but just an iron pipe, I think galvanized iron. I cut one here. You wrap the same wire around it 20 or 30 turns, go through one end of the wire through the same 0.47 nanofarad capacitor into the base of the transistor. Now when you take the wire from the bottom of the secondary coil, which is feedback, and just touch this iron anywhere, the light comes on. So you can do it with any piece of iron really, even this pipe. You can also do it with a small aluminum tube of about 10 millimeters, although it's not quite as safe. You take the wire from the secondary coil, touch the aluminum tube, and then induce magnetic fields in the aluminum make the light turn on. This wire is very hot when I was just touching it, and I was touching these wires, they don't hurt you at all. For those of you who want some more sophistication, here's another design of the same thing, maybe for industrial systems. You take two aluminum discs, each 3 millimeters thick and 100 millimeters in diameter, and you join them each with a wire and join the wires together. We're going to make a little aluminum sandwich here in a minute. And then you take a wire coil. This is monofiller, about 1.25 millimeter. The resistance of the whole coil is only about 1 ohms. And what we're going to do is we're going to make a sandwich. We're going to put the coil between the two plates like this. And then we're going to attach these plates to the bottom of the secondary coil for feedback. When we make an aluminum sandwich of this kind, where the two discs of aluminum are the bread and the coil is the cheese, then we attach the two discs of aluminum to the feedback wire coming out of the bottom of the tall secondary coil. Then we can take either wire coming out of the wire coil in the center, which is a long pancake coil. We come over here and we can touch it to the wire that goes into the base of the transistor through this 0.47 nanofarad capacitor. And we do that we see every time we touch it, the light comes on. So it's exactly the same as before. So this is a more elegant method for high power applications. Is this energy wireless or direct? The coil and the aluminum are not in any conductive contact with one another. If we lift the coil a little bit, the light doesn't shut off immediately, it just fades slowly as we lift the coil up. So we have a very short range wireless interaction, but it only goes for about a centimeter, and then it gets lost. When you take the power up to 20 volts, which is moderate, the transistor's warming up a little bit, but you're not going to get burned by anything using this feedback method, and go to the top of the coil, you can still see a test light coming on quite nicely at some distance from the device, out for about a foot. So plenty of energy is coming out of this coil, even though we're using these indirect feedback methods to stop from burning the transistors. Summary, I would recommend any of these safe methods when working with Tesla coils and transistors, like in the Slayer exciter. You won't get the transistor hot and you won't burn yourself either. This transistor is staying quite cool. It's been on for about 10 minutes at 20 volts. The light's very bright. And what that means is we're still getting some resistance heating in the transistor due to flipping, but we're not getting any heat from the feedback cable itself, which is undesired. We'll consider how this works for MOSFETs soon.